Welcome back, everyone, to MAE170. This is the second part for lecture 7. So finally, we're ready to talk about control systems stability. Everything that I will be talking about in this lecture will be in chapter number 6 of your textbook. So the main question that we want to answer is, given a system, and again, you can think about it just as a transfer function. Well, is the system stable or not? Well, before answering this question, let's try to understand the concept of stability by looking at a very intuitive and very common example that you're all very familiar with. That is the simple pendulum. All right, so here we have a simple pendulum that is fixed. So the pendulum itself is going to have mass m. It is subjected to the force of gravity equals to mg, always pointing downwards. Then we can have a drag force or friction force, which we're going to call Fd, that is always opposite to the motion of the pendulum. And then we have the tension force along the string or the rod connecting the mass with the pivot point, which we're going to call O. Furthermore, we have the length of the pendulum called L and the angle that it makes with the vertical axis equal to, let's just call it theta. So intuitively, we can think about the stability of the pendulum in this way. So if we perturb the pendulum from its equilibrium point, well, does it come back to it? If so, then the system is stable. If not, then the system is not stable. You might say, okay, well, simple pendulum, it is stable because if I let it go, after a while, it will come back to its equilibrium position. Well, that is okay if the equilibrium position is the vertical downwards one, but the simple pendulum has two equilibria. How do we know that? Well, we have first of all to write down the equations of motion for the simple pendulum. So here I'm going to go quite fast. So now the output of the system is the angular position of the pendulum. So what we've been calling y now is our angular position theta. So the equations of motion start by writing down the inertia of the pendulum I times the angular acceleration theta double dot, and this is equal to all the external momentum. So we have Fd times L minus mg sine of theta L, that is the contribution of the force of gravity. And then we don't have any other external forces. The tension T, since these equations of motions are taken with respect to the point O, the tension T does not provide any external moment. What we can do now is that we can substitute this drag force or friction force with the coefficient, and then we can take it proportional to the angular velocity. So we always write it as minus d times theta dot. The minus is because it's always opposite to the motion of the pendulum. And times m, L, and the rest remains the same. The inertia of the pendulum I, in this case, is equal to ml squared. And so dividing everything by ml squared, we have that theta double dot plus d over ml times theta dot plus G over L times sine of theta is equal to 0. So here we have the nonlinear equations of motion for the simple pendulum. Now, what are the equilibrium points of the system? Well, the way you would actually do it, you have to set the velocity and the acceleration equal to 0. And so all you have is sine of theta equal to 0. So the two equilibrium points are reached at theta equals 0 radians, and of course at a velocity of 0 radians per second. And the other equilibrium point, so this first one is the downwards position, and the other equilibrium point is the upward position, that is the angular position is equal to pi, or 180 degrees. And of course, the angular velocity is once again equal to 0. So since we have a nonlinear system, again, this is just a review of what we've already seen. We want to linearize the system. We want to linearize it about a reference point. Here we have two reference points, so we're gonna obtain two linearized systems. If we linearize about the downward equilibrium, we get theta double dot plus d over ml theta dot plus g over l theta equals 0. And then this has to be accompanied by two initial conditions. In this case, let's just assume that the perturbation is just position-wise. That is, we're going to give it an initial condition in terms of angular position that is different than 0, but with an initial angular velocity of 0. That is, let's say that you pick the pendulum, you give it an initial angular position, and then you just let it go. All right, so now we can write the same equations, linearized equation, but now for the the upward position. And now we're going to have a minus g over L times theta. Why do we get a minus? Well, if you go back to lecture 2, you would find out the reason why. Once again, let's pair it with the same initial conditions. Just one thing that I want you to notice is that now the initial conditions are referred to the equilibrium point. So right here, this theta 0 refers to, it's a perturbation from 0, from theta equals 0. Whereas in the other case, since the reference point is the upwards equilibrium, then this theta 0 represents the perturbation from theta equals pi. Then another few things. G is the acceleration of gravity, so it is positive. L is a length, and m is a mass, so G, L, and m are all positive. Now D, the damping coefficient, can be either positive if we are considering friction, or 0 if there's no friction or damping. Of course, in real life, there's always going to be some sort of friction of damping, but just for the sake of studying all the cases, let's also imagine that we can set the damping to 0. So going on with our example, which once again is a review also what we've seen so far, we can transform our equations of motions from the time domain to the s domain by taking the Laplace transform. So we have s squared times theta of s minus s theta 0. We don't have the theta 0 dot being equal to 0. Then we have plus d over ml s theta of S minus d over ml theta naught. And then here we're going to have either plus or minus for the two cases, g over L theta of S. And this is equal to 0. So here, just keep in mind that this plus or minus refers to the downward and upward position respectively. So how do we find the solution? We simply have to explicit theta of S. And so in this case, we have theta 0 times S plus d over ml over S squared plus d over ml S plus or minus g over L. Now, in order to use symbols that are familiars, we can call g over L with omega n squared. So omega n, that is the natural frequency, is the square root of g over L. And then we have that d over ml is equal to 2 zeta omega n. So omega n, the natural frequency, is always positive, and the damping ratio zeta is positive or equal to 0. Again, equal to 0 if we don't have any damping. All right, so with these symbols that we introduced, we can write or rewrite the output, that is the angular position in the S domain, times S plus 2 zeta omega n over the expression that is familiar now to us. And in the other case, well, it's pretty much the same, but with the minus when it comes to the last term of the denominator. All right. So I did all of this mainly because I wanted to review what we've seen in these weeks. And, you already know the answer, whether we're dealing with a stable or an unstable system. So we don't really have to take the inverse Laplace transform to get to the time domain, although I suggest you do it for exercise. What do we know? Well, we know that with respect to the downward equilibrium position, if we perturb the pendulum, then if there is a little bit of damping, eventually it will oscillate, the amplitude of the oscillations will diminish until the pendulum reaches again the vertical downward equilibrium. However, if the pendulum starts from its upward equilibrium, even a slight perturbation from it will make the pendulum sway away without ever coming back to the vertical upward position. So intuitively, we already know that one system is stable and the other system is not stable. So we'll know that the downward equilibrium is a stable equilibrium, whereas the upward equilibrium is a not stable equilibrium. But is there something that we can look at and tell this without relying on our intuition? Well, there is, fortunately. And as a matter of fact, it is all contained in the poles of the transfer function of the system. Here, however, we have the output of the system. We don't really have the transfer function, because the transfer function is the output divided by the input with initial zero initial conditions. So technically, we would have to build the output considering the input too. So the first part right here that I'm rewriting contains the initial conditions, and that's what we've derived. And this is what we've called the free response. And then we're adding the so-called forced response that depends on an input. So when you perturb a pendulum and just let it go, there's no input. But generally, you can also apply an input. In this case, an input means an external moment applied to the pendulum. All right, so since we do have the complete response of the system, we can find its transfer function. So transfer function, once again, output over input with 0 initial conditions. So the free response is not really considered. We simply have theta over r, and it is equal to 1 over s squared plus 2 zeta omega n s plus omega n squared. Now, you see that here the denominator of g of s, so the poles of g of s, happen to be the same of the poles of theta of s. And yeah, that's very convenient, but technically we should always look at the transfer function of the system, because if the input here, this theta s, if we had had an input that was, for instance, a ramp input, then we couldn't really look at the response because that would have extra poles due to the input itself. So we would just complicate things further. So all you have to do is take a look at the transfer function of the system, g of s. In this case, g of s. Why g of s? Well, because we don't really have a controller. We're not really talking about a closed loop. So we simply have input g of s output. All right, so I promised you that just by looking at the poles of the transfer function, we can infer some information about the stability of the system. So we need to solve the characteristic equation. That is, we take the denominator of the transfer function and we equate it to 0. Here, obviously, we have two characteristic equations because we have one with the plus sign and one with the minus sign. Now, since we're dealing with an actual example, let's put in some numbers. So we'll consider just a natural frequency of 1 radians per second and a damping coefficient of 0.5. So if we consider the downward equilibrium, that is, we have the plus for the last term of the characteristic equation, then the characteristic equation itself is s squared plus s plus 1 equals 0. So the roots of this equation, that is the poles, are equal to minus 1/2 plus or minus I square root of 3 over 2. You see that these numbers are complex conjugate, and we can place them on the s-plane right about here. We have P1 and P2. Now, if we plotted the response, that is the angular position of the pendulum, just given the initial angular position different than 0, and with the angular velocity equal to 0, we would find a response that looks like this. So it's an exponentially decaying harmonic function. So we have a harmonic function whose amplitude decays exponentially. And to visualize what happens, well, we'll have that the pendulum just swings, but then when it goes to the other way, it doesn't really reach the same theta 0 as the initial position, it will reach something less, and then it will swim back, and the amplitude would decrease until it just pretty much stops in the middle. Of course, that stops is between quotation marks because that technically happens only at time equals infinity. Nevertheless, we have a stable system. Now, what I want you to notice is the real part of the poles is negative. It's equal to minus a half. So it's less than 0. And this is going to be the key thing. Now let's take a look at what happens for the upwards equilibrium. So since we have a minus sign, now the characteristic equation becomes s squared plus s minus 1 equals 0. And so the roots of such equations, that is the poles, are minus 1/2 minus square root of 5 over 2. This is a real number, and it's negative. The second one, though, is minus 1/2 plus square root of 5 over 2. And this number is still a real number, but now it is a positive number. So let's first place the poles on the s-plane. We have P1 about here and P2 about here. So you see that P2 is positive, and so that causes the response to blow up to infinity as time goes to infinity. So if this red line represents the position, the angular position of the pendulum as time, as a function of time, we start at theta naught, and then just the angular position increases with respect to the vertical upward equilibrium indefinitely. Of course, for the real system, it doesn't grow indefinitely because it will just swim back, right? But since we're dealing with a linear system, this is just a linearization of a nonlinear system. So all it matters is that it'll just go away from the equilibrium and it will never come back to it. So the key thing here is that we have a pole that is positive, or whose real part is positive. So we can start to see a trend here. Now let's take a look at another case. What if we had FD equals 0? So in other words, what if we didn't consider the friction or the damping? And in this case, the damping coefficient is actually equal to 0. So the downward equilibrium's characteristic equation becomes s squared plus 1 equals 0. And so what are the roots of such equations? Those are plus and minus I. Plus and minus I are on the imaginary axis here and here. So we have P1 and P2. And if we plotted the response of the pendulum when we let it go, well, the pendulum without friction to slow it down will keep oscillating between plus and minus theta 0. So the response is a purely harmonic function. Is this a stable system? No, it's not, because we're never coming back to the equilibrium position. We just pass through it an infinite amount of times, but we will never converge to it. So even this case is not stable. And be very careful here with the words. This doesn't mean unstable. Not stable and unstable are not synonyms, as I will tell you in a bit. So not stable means that it's not stable. If it's not stable, it's not stable. That's it. But it doesn't necessarily mean unstable. All right. Well, what about the upward equilibrium? Well, we already know that that's still unstable, but let's prove it. So now without the damping coefficient, the characteristic equation is simply s squared minus 1. And so the two poles are +1 and -1. On the S-plane, we can visualize them like so. So we have P1 and P2. And once again, the response will just go to infinity. So if let go, the pendulum will just go indefinitely away from the vertical upward position. So once again, here we're dealing with a non-stable system. And if we look at the poles, once again, we have that one pole has a real part that is positive. Probably I haven't really, I haven't said anything about the undamped case for the downwards equilibrium, but the real part is 0 here in this case. So it's not negative. So now we're ready to actually state the necessary and sufficient condition for the stability of linear systems in terms of the poles. So if we have a linear system, we can find its transfer function. And when we look at the poles of the transfer functions, if all the poles have negative real parts, or if they lie on the left-hand side of the S-plane, then the system is stable. So stable system implies poles of the transfer function with negative real part, and negative real part of the poles of a transfer function implies that the system is stable. Now notice that this condition, which I've numbered with 1, is very similar to one of the two conditions that we've already encountered when we defined the applicability of the final value theorem. It's not really the same, because for the final value theorem, we wanted all the poles to have either negative real part, or we had an exception for just one pole at the origin. For linear systems to be stable, that cannot be the case. We cannot even have even one single pole at the origin. So the condition for the stability of linear system is a little bit stricter than the condition for the applicability of the final value theorem. And the only difference is in the pole at the origin, with whether it is allowed or not. If we have one pole at the origin, then we can apply the final value theorem. But if that was the transfer function characterizing a system, that system would be not stable. Now, there's another alternative definition for stability, and this gets a little bit more mathematical, but I think it's very important that you see it and don't get scared. It looks nastier than what it actually is. Let's read it together. So this condition states that a linear system is stable if and only if the absolute value of its impulse response integrated over an infinite range is finite. All right, so let's take a look at what this definition means. So a linear system, we're familiar with that concept, is stable. All right, it's just the definition. If and only if, when you encounter if and only if, that means a necessary and sufficient condition. So it means that what comes after, if that applies, then the system is stable. And you can also go the other way around. If the system is stable, then whatever follows applies. Now, the absolute, we have to check the absolute value of its impulse response. So we need to find the response of the system due to an input that is equal to an impulse. We have to take the absolute value, And then we have to integrate from 0 to infinity. That's what over an infinite range means. And if this integral is finite, then the system is stable. So if we have an input that is equal to an impulse, then due to the convolution integral, the output is equal to minus infinity, from minus infinity to t of g of t minus tau, where g is the transfer function, times delta tau d tau, and this is conveniently equal to g of t. So for an impulsive input, the output is equal to the transfer function even in the time domain. So g of t represents the response to an impulse. Now, the system is stable, so you can also sometimes you can encounter this just saying g of s, so the transfer function of the system is stable, but what it really means is the system itself is stable. IFF, if and only if. Now we have to take the integral over an infinite range, that is from 0 to infinity, of the absolute value of g of t. And we have to check that this is less or equal to a constant. So it has to be a finite integral. So this, in this case, m is a real number. So you can either use definition 1 or 2. They are totally equivalent. Let's take a look at some examples. So if we had a transfer function of 1 over s plus 2, now let's take the Laplace inverse transform of this. So g of t is equal to e to the power of minus 2t. Let's take the integral from 0 to infinity of e of minus 2t dt. So since e of minus 2t is an exponentially decaying function, it's always positive, so we don't really need the absolute value. So we can simply calculate the integral from 0 to infinity of its argument. And this is simply equal to minus 1/2 times e to the power of minus 2t integrated from 0 to infinity, which gives us 0 minus 1/2, so it's plus 1/2. And so this is definitely, it's a finite number, so m can be taken to be equal 1/2. 1/2 is a real positive number, so system is stable. Let's also apply definition number 1. Well, we have the transfer function g of s. Let's calculate its poles, or in this case, its pole, because it's only one pole. The pole of g of s is equal to minus 2. Minus 2 is a real number, real negative number. So we are done. The system is stable. Let's take a look now at another example. Now we have g of s equal to omega over s squared plus omega squared. In the time domain, we have that this is simply a sinusoidal sine of omega t. Now let's apply definition 2 first. So let's take the integral from 0 to infinity of the absolute value of g of t in dt. And so instead of solving it mathematically, let's just solve it graphically. So what we want to do is, first of all, let's draw sine of omega t. And in this case, it's the blue line. Let's take the absolute value. So we're flipping all the negative to the positive, on the positive side of the plane, and the integral of this function is just the area under such function. So we have this area plus this area plus this area, and so on and so forth until infinity. And you see that here we're adding the same number, because it's always the same area, for an infinite amount of time. So this area, this integral, is just infinite. So this system is not stable according to definition 2. Let's take a look at the poles of this transfer function, and let's see whether or not definition 1 agrees with definition 2. So obviously, using definition 1 is way easier in this case. So we have the P1 and P2 are equal to, we have to solve what? S squared plus omega squared equals 0. So P1 and P2 are equal to plus and minus I omega. And you see that the real part is equal to 0. So it's not negative. Therefore, the system is not stable. The conclusions drawn from the two definitions match. All right, so as a recap, we saw that a linear system can be, or is defined as, stable if the system transfer function has all poles with negative real parts. Now, this stability is also known as asymptotic stability. So sometimes you might encounter the definition, or the same definition, but saying a linear system is asymptotically stable. It's the same thing for linear systems. Now, as I said, if at least one pole doesn't have a negative real part, then the system is not stable. Now, if the system is not stable, it still can be what it's called marginally or neutrally stable. So it's almost stable. And this is what's described in this following definition. Let's read it together. A control system is marginally stable if it has at least one pole on the imaginary axis, with multiplicity that is at most equal to 1, and all the other poles have negative real parts. So in this case, we can have, the definition is a little bit less strict. We are allowing poles not just on the left-hand side of the S-plane, but they can also be on the imaginary axis, as long as their multiplicity is equal to 1. So we cannot have repeated poles on the imaginary axis. We can have repeated poles with negative real parts, that's fine, but we cannot have repeated poles on the imaginary axis. Otherwise, the system is not even marginally stable. But again, if all the poles are either on the left-hand side of the S-plane or on the imaginary axis with multiplicity at most equal to 1, then the system is marginally stable. And that is equivalent to the pendulum without friction, just swinging from plus theta 0 to minus theta 0. So it's just a sinusoidal response. Now, if nothing in case 1 and case 2 is met, then we have case 3, which the system is called now unstable. So an unstable system is a particular case of a non-stable system. So an unstable system is a system that is neither asymptotically stable nor marginally stable. So it means that it has at least one pole with positive real part and or has poles on the imaginary axis with multiplicity greater than 1. Let's take a look at some examples. Once again, here's just a reminder that the poles are the roots of the characteristic equation. The characteristic equation is the denominator of the transfer function equated to 0. So let's visualize examples of, for instance, an asymptotically or simply a stable system. So a stable system can have poles like so. All of them lie on the left-hand side of the S-plane. None of them are on the imaginary axis nor on the right-hand side of the plane. So the system is a stable system. Now let's take a look at a system that is marginally stable or neutrally stable. So here we can have poles on the imaginary axis. Of course, they always, if they are complex, if they have an imaginary part that is different than 0, they always come in conjugate pairs. So let's say this system is marginally stable because it has poles on the imaginary axis with multiplicity at most equal 1. Now, this system might look similar to what we just drew, but now we have the two pairs of imaginary poles are repeated. So here we have a multiplicity equal 2. So this implies that the system is unstable. Another example of an unstable system is, no matter how many poles we have on the left-hand side of the S-plane, well, as soon as we have one pole on the right-hand side, the system is unstable. And remember, the key is that the response linked to a certain pole or pairs of complex conjugate poles is proportional to e to the real part of the pole. So if this real part is positive, then e to something positive times t, when time grows to infinity, then this contribution also grows exponentially to infinity. Now here, a quick example of the unstable system that we saw over here. Well, not exactly the same, but a similar one. That is, we have a repeated pair of imaginary poles. In this case, we have P1 and 2 that are equal to plus or minus 2i. But then we have P3 and 4 that are also equal to plus or minus 2i. So we have imaginary poles with multiplicity equal 2. And in fact, if we apply, let's say, an impulsive input and we take the output in the time domain, and here I just give you the answer to that, you'll see that there's this factor t that grows, and in this case grows linearly. And so the output is a sinusoidal wave, but which the amplitude grows linearly all the way to infinity. All right, so the lesson that I want you to remember from this is that in order to check the system stability, all we need to do is, if we don't want to use the more convoluted definition too, we can just simply look at the transfer function of the system, compute its poles, and check their real parts. If all the real parts are negative, then the system is stable. Great. We want stable systems. Now, sometimes the poles of a transfer function are quite difficult to compute. And this is, of course, this comes from the older days, because now with MATLAB, it's really easy to find the roots of a function, of an equation, even of a very high order. But you have to remember that sometimes you might just want to find the stability of the system. And let's say you don't have a computer with you, or if you just want a quick analysis of a system, you might want to have other tools available with you. So this system, or this other criterion, this alternative criterion to check the stability of a system, was developed by Routh and Hurwitz. And so it is known as Routh-Hurwitz criterion. So this is an alternative criterion to check the stability of a system without having to compute the poles of the transfer function of the system. And this might look longer, but it's actually much simpler. And again, this was developed when the computers were not powerful enough. So, if you don't have tools, you have to use your mind, and you have to come up with solutions, which are very, very brilliant most of the times. And that's exactly what happens here. So let's take a look at this criterion. All you need to do is to consider the characteristic equation, that is, our d of s equals 0, and we can write it down as our polynomial equation. So we have an times s to the power of n plus an minus 1 times s to the power of n minus 1 plus a2s squared plus a1s plus a0 equals 0. So all these a's, which I called ai, are real coefficients, and I goes from 0 all the way to n, where n is the degree of the polynomial. Now, the first thing that you want to check the sign of all these coefficients. So this is just a necessary condition, but it's not sufficient. That is, all right, so let me write it down. All the ai coefficients must have the same sign. So that is, they must be either all positive or all negative. We'll just consider all positive. You can always multiply by -1, and even if you have them all negative, they'll become all positive. So let's say that they must be all positive. This is a necessary condition, but it's not sufficient. It means that you can have a characteristic equations with coefficients that are all positive or all the same sign, but still but yet the system can be unstable. So again, this is not necessary and sufficient, but it is necessary. It means that if you already see a sign change, then you already know that the system is not stable. So you don't have to go through all the Routh-Hurwitz criteria, because it can get a little bit time consuming. And speaking of time, I think I ran out of it. So we'll take a look at how to build a Routh array next time, but please take a look at the steps. It's only really 4 steps. And then I've included a couple of examples, and we'll cover them next time in details. But if you already take a look at them, it's probably going to be easier for you to follow. All right, so I'll see you virtually next time, and take care. Bye-bye.